Does not make any difference, I'm sorry. So that you're already connected and everything is all set up, so you don't have to get out and get in again. Is it all right with
Yeah.
you?
I'm fine, but I thought the talk was at noon, right?
Um, I'm sorry, I could not hear you. What did you just say?
Yes, my talk is scheduled for 5 p.m.
Che cosa? Sì.
Okay, welcome back, ladies and gentlemen. We can start this second part of the afternoon session. And we have two talks. We decided to swap the two talks that have been planned. So we have Professor Joseph Silk, which is online, and everything is ready for his talk. Professor Silk is from the Johns Hopkins University and Institut Astrophysique de Paris. The title of his talk is, as you can read, Radio Telescopes on the Far Side. So I invite Professor Silk to start whenever he is ready, and thanks for joining us.
Good morning, everybody. I'm so sorry I can't be with you in person, but I'm going to make the case for doing cosmology from the moon, focus very much on radio telescopes on the far side, but say a bit about the potential of other telescopes, and above all, emphasize how important it is to keep in mind that the astronomers will need a fairly pristine environment in certain senses that I will explain as we go along. So let me begin. In the beginning, so the universe, we think, we're pretty sure, but we have no direct proof, began with a state of immense inflation. It's a real challenge to find evidence for this. One piece of evidence comes from the microwave background, where we have these many fluctuations of quantum origin, actually, associated with the end of inflation. And they then develop into density fluctuations that eventually form galaxies by gravity, their own gravity, as the universe expands. And we run into the present universe eventually, this beautiful thing we're exploring now with the biggest telescopes, with many, many billions of galaxies and black holes and so forth. What we are trying to understand is what happened at the beginning. Before any galaxies, there were the dark ages. We have no clue about that at the moment. It's an expectation that there were hydrogen clouds there. The building blocks of galaxies, as you can see in this cartoon, are building blocks, and we should be able to see those in shadow against the microwave background if we can look in the characteristic band of hydrogen, neutral hydrogen, which is at 21 centimeters. But of course, highly redshifted from this very early epoch in the universe, millions of years after the Big Bang. So that is the incredible challenge that we have. And there is yet one more big question, which I'll address briefly, namely, even at the very end, we have no idea if we are alone in the universe, and that also is in a certain sense, an aspect of cosmology too. And I'll explain how the moon is going to come to our rescue most likely with these projects. So current progress in cosmology is very, very frustrating. I'm just going to review for you all that we're actually doing in cosmology now and try to explain that we're running into, well, we have a wonderful future. We're building bigger and better experiments, but we see no imminent signs of success, and not even can we imagine any guarantee of success. So first, in the top left, you see our attempts to measure the equation of state of the universe. This mysterious cosmological constant gives us a current acceleration that's controlled by the equation of state, a slightly negative equation of state today. As predicted long ago by Lemaitre, we have many wonderful telescopes. You see three of them, Euclid, Roman, and Rubin, which will do future surveys, but with no guarantee of success. The microwave background should carry an imprint of inflation from polarization. Again, the models are all over the place, really. If we're lucky, we'll get a strong enough signal to measure, but we may not. No guarantee. Dark matter, likewise. enormous parameter space. We don't know what the cross-section of interactions of the particles is. We think it consists of weak particles, it's our best bet, but we don't know the mass also. With this huge parameter space, we're probing small bits of it with wonderful experiments in space and underground, but again, no guarantee of success. You could go to the particle physicists and say, well, let's crash particles together at much higher energy. Maybe we'll produce dark matter particles. Who knows? That's one of the goals of the next future collider at 100 TeV center of mass energy. But with no guarantee it'll find anything new. And finally, maybe gravity is completely wrong. Maybe there's a new gravity out there which could explain some of the tensions we have at the moment in cosmology. Again, there's a vast parameter space to survey. We've only sampled a tiny bit and verified Einstein's theory, but we just have no guarantee that this is the right theory. What can we do in science that will give us a guaranteed return? That's what we want. Future experiments with a guaranteed science return and compelling science return. So I'm going to argue to you that the far side of the moon is the most natural place to do low frequency radio astronomy. We just simply can't do it from the Earth because of the Earth's atmosphere. The moon happens to be the ideal place. It's the most radio quiet environment in the entire inner solar system. There's no ionosphere, so we can see at these highly redshifted frequencies to look for the 21 centimeter line of hydrogen far in the past at these low frequencies, and there's no interference from terrestrial television receivers, maritime radars, all the usual things. So it's a great place to go. It's ideal. It's a unique place, really. And then what are we going to do? Well, this is the way it works. We're looking for a shadow against the microwave background from this hydrogen in the dark ages, long before the galaxies formed. This is the new frontier of cosmology. With our big telescope, we've pushed forward to see even the first galaxies now. But before then, we just don't know, and that is the next big thing to do in cosmology, really. It's a huge new horizon. And just to show you the power that we have by doing this, because the microwave background, wonderful resource of cosmology, is limited by basically 1 million pixels on the sky, 1 million points of information, if you like. Large scale structure, we can do better. We have billions of galaxies in our future surveys. But really, galaxies are sort of not the most perfect things to use, so we average over them. And the amount of information we get back is limited only by going to radio, where we have all these building blocks, these clouds. We know what their typical masses are. There are 1 million solar masses. There are, billions of galaxies out there, and therefore huge numbers of modes in principle in these clouds. That's the way we can do precision cosmology. And to just try to ram this home a little more, going to the moon, we can do this. No ionosphere, no interference from radio, etc. What are we going to do? Well, at 21 centimeters, it's redshifted. We're talking about going back to so far away that the 21 centimeters becomes 10 meters or 30 megahertz. What we want to do is examine this for these tiny fluctuations seen because the hydrogen is colder than the microwave background, seen as tiny shadows on the sky. This really involves, it's very, very hard, but the point is that we have all these pixels on the sky. In the radio, you can see it's 1 million times more powerful. If I take the square root, of course, 1,000 times more powerful than basically the microwave background. So we can do amazing things. The problem is going to be the foreground, which are incredibly bright. All those relativistic electrons emitting synchrotron radiation between us and this very high redshift in the past. So what can we do about that? Well, I'll show you our telescopes strategy in a second. But with all this information, there's one amazing science goal we can do that's even probably more profound than just seeing through the dark ages. This is inflation, the beginning. And that's because you have so much power in these tiny points of information. If you can resolve this, you need a big telescope, you need an interferometer perhaps to get the resolution, millions of dipoles, antennae, these are 10-meter wavelength waves we're looking for, so typical television type antennae will do. And then we look for this signal, this twisting of the fluctuations, which is a unique prediction of inflation through primordial non-Gaussianity, and we have a prediction of how small that should be. It's a fraction of a percent. That's probably 100 times better than we will achieve with the next generation, with any generation of galaxy surveys. So we can't do it with galaxies or the microwave background, but we can do it with these hydrogen clouds because there are so many of them. And we're going to look for signals on the radio sky that would detect these twists due to primordial non-Gaussianity, which is a unique prediction of the inflation theories, the whole set of inflation theories that we're trying hard to distinguish between. So that's the future for cosmology. And the amazing thing is, all of this is happening now. We're on the way. So it began just 4 or 5 years ago with China launching a dipole antenna to look for the dark ages on the far side. Unfortunately, it had too much local radio interference, and so it's studying the terrain, but not producing science. There will be a NASA mission to be launched. It's under construction now in a couple of years, which will be a similar experiment to the Chinese one, but this time carefully designed to give us a dark ages signal if they can stay on the moon taking data for long enough, because it's very cold, they need extreme battery life, etc. So it's the first mission that may have a real chance of doing something, but it will surely be the precursor to many others. And indeed, there is another mission also on the same time scale being prepared in China, which has 9 small satellites, each with antennae orbiting the moon, with a mother satellite sending the data back. They take data on the far side. It takes an hour or two for the orbit, and then the data is sent back to Earth. So that also is intending to search for the shadow of the dark ages on the microwave background. It's a race again, and that's not the only race in space, as you'll see in a second. But before I get into that, let me just tell you about the future of radio telescopes on the far side of the moon. We know how to do this. We've put millions of dipoles, well, hundreds of thousands at least, are being put together in Australia as part of the SKA, Spherical Array, low frequency. But you can't get to low enough frequencies. Of course, on the Earth, we want to get below 50 megahertz. And you can build huge telescopes too. Again, on the Earth, the current record holder is 500 meters across. Why don't we apply some of this technology to the moon? Well, we begin small. These are design studies that will surely, some of them be chosen to be implemented in the next decades on the moon. A US design involves 100 antenna. A European design involves thousands. A similar Chinese design on the far side, several hundred antennae. And the more dramatic ones actually involve construction of antennae on the far side, local construction, and they hope to get hundreds of thousands of antennae. This is what you need to get the resolution with these 10-meter dipoles, basically, to zero in on the shadows that I talked about from the many clouds, the fluctuations. After you get the global signal, which the immediate experiments will do, that was like the discovery of the microwave background, if you will, then you go for the fluctuations, which is a long, long voyage into the future, but we're determined to do it. Okay, and then to aid all of this, you need to basically sort out these nasty foregrounds, and that you do by building a huge again, fast style, Arecibo style, dish if you are inside a lunar crater, which will give you the sensitivity to sort out some of the foregrounds. That also is a project for the future. Filling a crater with wire mesh and having the receiver span from the rims of the crater across it. That's what we intend to do. Okay, I'm going to say a few words about other aspects of cosmology and more. One is the microwave background radiation. We have this wonderful black body, maybe the best black body you've ever measured in the sky anywhere, in the laboratory even, from the sky. The 3-degree Kelvin radiation, incredibly perfect, but that's a total illusion. We know that the real universe is a complete mixture of fluctuations, explosions, all sorts of things, evaporating black holes, many, many things, particles annihilating with each other, weakly interacting particles, dark matter stuff, all these things speculated, but some of it must be true, and it should lead to deviations in the black body spectrum. Unfortunately, it's very hard to get this. The Kobe experiment, their FIRS microscope spectrometer set limits of parts in 10,000. We need to do 100 or 1,000 times better. What will that do? That will tell us that here's all the stuff that we know about in the universe. On the large scales, this is like a power spectrum. On the small scales, we just don't know. We assume there's lots of small stuff there building up to the big stuff, but we haven't. It's very hard to measure. We see the output as small galaxies, but these fluctuations tell us that we really had a bottom-up theory, basically. And so how do you test that? Well, this is what you're going to have to do. You're going to have to put a far-infrared spectrometer on the moon. Typically, you do that in a very cold lunar crater. The ones near the poles with such high rims around them are permanently dark and incredibly cold, down to 30 Kelvin. It's quite amazing. The ideal space to build interferometers that are going to look for deviations in a 3-degree Kelvin spectrum. So that's the sort of thing we want to do. We'd need a small telescope, 1.5 meter telescope, and you'd let, as the moon rotates, you'd scan the sky, and you'd compare a reference black body with the black body on the sky in the thousands of gigahertz range. So that's the plan for the future. But again, it's something that probably only the moon can allow us a forum to do this, just because a free flyer in space would be, it's another option, but it would be very expensive, and it would be wonderful to include this as part of our lunar program. And that, of course, again, would mean protecting the moon, as I'll come to in a second. So that's the hope. And then finally, on telescopes, I cannot avoid mentioning the fact that we can do amazing things with telescopes on the moon in principle. First of all, when it's come to building telescopes on the Earth, the biggest one that we'll ever build is almost certainly the 39-meter ELT. That's great. That's going to revolutionize astronomy in a few years' time. But it's not going to get us into finding evidence of life or whatever on distant planets, exoplanets. NASA is planning a 6.5 meter telescope to do just that. But the reach of this telescope is such that you probably will see very few tens, the estimate is 25, Earth-like twins nearby to go into in further detail. If you had a much larger telescope, you could get thousands of these things, and that would get you far on the way to seeking evidence for life forms. Putting telescopes on the moon has been done. The Chinese have one already that's been operating for a number of years. It's a very small one, but we need to do something that's more dramatic. One dramatic thing would be to do an infrared telescope. This is, again, a design study of something that could do tens or hundreds of times better than the James Webb telescope, because the moon has no atmosphere. It's a wonderful place to do infrared astronomy. But that's not all. Here is maybe the most incredible thing to do, and that is go to a crater like this. Here's an example of a crater with such high rims that they're permanently illuminated, be it inside you of eternal darkness, down to 30 Kelvin temperatures, 20 odd kilometers across, 4 kilometers deep. What this scheme proposes to do is to have an interferometer, many individual meter, 5-meter telescopes, hundreds of them on the rim, cables from the rims with the camera. And this would be a hemispherical mirror. It would be a wonderful thing. And with that, you get amazing resolution. So here's an artist's view of what you could find. Go to the nearest star system with many Earth-like planets, that's the TRAPPIST system, 40 light years away, and you could get resolution like this, incredible resolution. And look for oceans, mountains, whatever, even, signs of illuminated cities, if such things ever existed. A wonderful thing to do. Okay, so now let me end with the politics and what is happening on a large scale. There's a whole current renaissance in lunar science, thanks initially to the commercial sector. So these companies are all providing modest-sized spacecraft to put experiments on the moon. I showed you one example of what is being done with one of the first Dark Ages experiments. But we can do much better, we will do much better. Why? Because we're building these incredibly large rockets with up to 100-ton payloads delivery on the moon. They're incredibly expensive at the moment. This is the NASA SLS system about to undergo its next launch to take astronauts around the moon in 2 years' time, perhaps, and then eventually land on the moon. But it's, the budget is huge. $500 million estimate is what it will cost. It's not something for the scientists to really venture into with sums like this at stake. But there are other spacecraft under construction. Starship is one, New Glenn is another, which will have similar payloads. But what these promise is recyclability. They'll be reusable. And this brings down the cost to something feasible, tens of millions of dollars per launch, it's estimated. And then once we have these things, but even before we have them probably, this is even planned for the SLS, ESA is constructing a lunar lander which will be taken there, and it will have 1.5 tons of cargo space. You can imagine it'll be a little bit like having Amazon delivery onto the moon to do science experiments. Now, what the telescopes I've talked about, the big ones, are really, really expensive. But what you have to remember is that it only takes a few percent of the budget for the moon, for Artemis and all of that, to do all the science that we might possibly want to do. And we'll have robots to help us too. So that's the budget message. I'll return to that in a second. Here, in fact. So you can see this is the, as an example, the NASA budget. This was the Apollo 50 years ago. Apollo was an immense effort, pioneered by President Kennedy at the time, and that led to some 17 astronauts walking on the moon, basically. But since then, the budget's gone down naturally, but this budget still, the current budget, is enough to fund the Artemis program, and that envisions, so going from our one tracer left on the moon, going to the future, we have an Artemis including a space station around the moon, the gateway, and bases on the moon, eventually industrial construction on the moon. So why not telescopes? That's the hope. Well, so they will do compelling science. I think there's a strong case to be made. Okay, so I'll end with the real problem and one of the key points of this conference. Namely, we do have the United Outer Space Treaty from 1967. It was a great success at the time, and it discussed issues like pollution on the moon, military activities on the moon, but there are amazing gaps. And the major gap is that we have no way of enforcing anything on the moon. So what we somehow have to avoid is pollution, debris, etc., and also competition, because here we have, for example, the number of useful sites on the moon for the experiments I've talked about, the big ones. You need decent-sized craters, etc., with very smooth and mild slopes. There aren't that many of them, and there'll be a competition with commercial interests. There'll be mining proposed for the moon. We scientists will somehow have to sort out that their activities do not pollute the moon too much, and etc. And right now there is no enforcement at the moment, and we're essentially looking at something like the Wild West all over again, and hopefully we're going to come together internationally to avoid all of this. So let me finish. The future of cosmology, what were our origins, the future of astronomy, are we alone? These are the biggest questions we have in all of physics, certainly, and beyond, and I think we will answer these by doing experiments on the moon, and that's the hope. We're going there for many reasons. I think science beckons as one of the activities we should be doing. It's always been true in the past when we undergo new explorations, and we have to negotiate now for a pristine lunar environment. Thank you.
Thank you, Professor Silk, for your presentation. So we have a few minutes for questions from the audience. Okay. Okay, we have one question.
Please present yourself before your question. Hello, good morning, Professor Silk. This is Dario Kubler from Italy, and my question is about a possible extra research based on this radio telescope that are going to give us a better understanding about the Dark Ages. Do you think this kind of research will also help us to understand how the big bubbles between the galaxies that we are discovering nowadays has been formed? I mean, the bubbles full of emptiness.
I'm sorry, could the presenter, the chairman, repeat the question? My sound is very bad, and I didn't get much of that. Could you repeat that, please?
Hello, can you hear me better now?
Now is good, yes.
Okay, sorry. So my question is about a possible result of the research on the Dark Ages related to the existence of these huge bubbles between the galaxies that we have discovered recently. And do you think the research on the Dark Ages will also help us to better understand why those bubbles has been created? Thank you.
Yes, so the bubbles basically refer to when the universe was reionized. We call that the cosmic dawn. And so the initiation of those bubbles comes from the first stars that formed. The Dark Ages takes us back even further backwards in time, before there are any such bubbles, but it will illuminate where the first structures are that are forming, where there's more power in the fluctuations, and these are destined to be the first sources that illuminate the universe and create the bubbles. So yes, the Dark Ages studies will essentially enable us to understand the origin of these vast superbubbles.
Okay, thanks. Any other question? Quick one? No? Okay. So there are any other questions? So let's thank again the speaker, Professor Silk. Thanks.
Thank you very much. Thank you very much.
And now we have the last presentation held by Dr. David DeBoer from University of California, Berkeley. And the title of the presentation is Techno-Signatures from the Lunar Farside. So we can try to upload.
Professor Silk, can you stop sharing your screen? Thank you very much. Oh no, c'era già.
Grazie.
Okay. You're way perfect.
You can use the.
Yeah, thank you.
Go.
All right, well, thanks very much, and thanks for the organizers for allowing me to come and talk about this. Fortunately, technosignatures has already been introduced and looked at from a few different perspectives, and we've seen with Joe's talk really the aspirational future of technosignatures on the lunar far side. I'm going to be a little more prosaic. I'll first introduce technosignatures, kind of how it's done currently, and why we need to go to the moon, and then talk about at the very end a small project, a kind of an early project that we're pushing, that we're trying to get going to go to the lunar far side. All right, so in many ways, SETI can boil down to this statement. You know, wouldn't it be a shame if we were being transmitted to and no one just looked? And that's kind of an interesting premise. That'd be kind of cosmically embarrassing, I guess, really. I mean, we couldn't hold our head up high when we finally get discovered. Now, we don't need them to be deliberately transmitting to us, but that's probably the strongest signal. And we should leverage some of our resources to searching for this. Again, we don't want to put countries out of bankruptcy, but some amount of resources should go to this. Now, of course, people are looking, and in fact, most of the resources that is going to looking for life outside of the Earth is in, with NASA and other space agencies looking for what we typically call biosignatures. You'll see that with the appellation technosignatures, we're actually trying to mirror that terminology, and it's actually more appropriate than SETI, but technosignatures is sort of synonymous with SETI, although we aren't trying to find intelligence per se, but we're trying to find technological manifestations of intelligence. So we like to go to the solar system bodies, and we want to go to more to do in situ sampling, and this would be potentially for life precursors or early life or alien artifacts. You know, we want to keep an open mind on this because we don't know where success is going to come from. And we're also building telescopes to look for and atmospheres from outer planets that will look for early life, you know, the burping bacteria that started oxygen on the Earth and so on, but also could potentially see things from an industry. So it, in some sense, is a technosignature. But in many ways, or in some ways, you can see that the limitation for these, which has already been mentioned, is the reach. So for in situ sampling and, you know, looking for things, we're kind of limited, well, we are limited to our solar system, and in fact, just the inner solar system, and hopefully soon more in the outer solar system. And it was as mentioned for these telescopes that will be looking for habitable planets, it's only within a few dozen, within a few hundred light years. So maybe they have a higher degree, higher probability of success, we don't know. There are no priors to any of this, but the sample size is actually quite large. But fortunately, there is a way to have a much bigger sample, and that's by realizing that we transmit a lot of energy into space. And here are a few examples of things that happen essentially every day that we transmit to space that are potentially accessible by nearest neighbors. And conversely, if they were doing the same thing, we would have a high chance of seeing this. In fact, if you take this to the extreme, the beautiful Arecibo telescope, and I'm going to keep this image in because we should pay homage to this wonderful facility, is the strongest transmitter that's ever transmitted from the Earth. And it could quite easily be seen at the nearest star, and in fact, even further. And if you really extrapolate to a really dedicated effort, we could receive that transmission a good chunk of across the way of the galaxy. So in fact, the whole galaxy is at our disposal to look for technosignatures now, if we are smart about it. Of course, if we only knew when and where to look, it'd be pretty easy. But unfortunately, we don't. And so we have to, and there are no priors for what we want to do here. So we have to figure out how we're going to approach this. Now, we don't know any of these things, so we want to target a couple things. One, what can we do now? You know, we're not going to wait for tachyon discovery to figure out that's how ET transmits, because we don't know how to do that, and we don't even know if that's real. So we want to do what we can do now. We want to do what we can do well. And we want to figure out how much we can afford to do and how much we want to spend. And then we always want to keep an open mind and learn and expand those techniques intelligently, as well as explore other new parameters that might come to life. So talking a little bit about what we can do now and what we can do well, I'll introduce the Breakthrough Listen program, which is one of the key programs I'm involved with. The Breakthrough Listen program is meant to be a transformative SETI program, 10 years, $100 million. We're into year 7, and I like to think that we're a lot of success in transforming the field of SETI. Specifically, our targets are to look at 1 million stars at quite high resolution and sensitivity, a galactic plane survey of the Milky Way. This would be more at low frequencies, as well as looking at galaxies. Who knows? There could be a signal that's so, maybe someone says, we're going to annihilate the energy that from the sun, entire star, and transmit it to another galaxy. But now we're looking at all the stars in the galaxy at one time. I will point out that 1 day of breakthrough listen is equivalent to a year of previous research, and that's like the best year of previous research. And we have made all this data public, or as much as we can. And if you want to get involved and look at the data, there are a lot of open source tools, and we really encourage people to look at the data and use our tools. The Breakthrough Listen program is headquartered at the University of Oxford. It had been headquartered at Berkeley, but as of late last year, we've transferred the headquarters to Oxford, which is a wonderfully supportive environment for this science. Now, we have these specific goals, but we have a few other important goals, and one is to help establish a global, sustainable scientific community for SETI. You know, we need the academic infrastructure. We need to have viable science outputs, train students, train postdocs. These become professors and actually go and do credible science and keep that sustainable. We also have an aspirational goal of every telescope on the entire planet all the time. You know, I think this is going to be a good chance of success. So we always encourage partners. We help fund kind of startups for partners to do SETI commensally. Commensal just means you're going to be looking anyway. You might as well put that into a SETI processor and see if you see anything that pops out. So the Breakthrough Listen, in fact, almost all SETI's primary approach is to look at stars. Now, when you're looking at stars, you're also looking at their planets and moons, which is helpful. So it's kind of good bang for buck. Now, we know where stars are. That's great. We can point our telescopes in specific spots. And it also seems credible that at least life started on planets around stars. It probably, you know, a million-year-old civilizations probably migrated well off that planet. But it's probably likely that life that has the same metabolic structure that we have, at least, is located there. We favor big telescopes because that gives us more sensitivity, more bang for the buck. And we look at frequencies on the atmospheric window, which has already been brought up before. There's the visible one is there, as well as the large radio optical open window. I will point out we aren't just doing radio, we're doing optical, but we're starting off as radio astronomers, so we tend to focus on the radio side, and we're trying to get more into the optical astronomy. And also right now we don't try to look through RFI because it's hard, if not impossible, to do on a tiny signal. So we look for places in the spectrum with minimal RFI. So you can say, well, you're limiting yourself. You're not looking everywhere all the time all at once. Well, it's because technosignature detection is hard. Even if they want to be found, even if they're beaming toward us, unless they're like really close or just parked on the far side of the moon, you know, who knows, it's going to be hard to detect. So for now, we focus on likely sky locations, available frequency bands, and simple modes, primarily drifting continuous wave modes. I actually took this out and put it back in. So our primary approach is to have large antennas, so large diameters. Area goes as the square. That does mean our field of view shrinks. It's a Fourier transform relationship. As you see more sensitivity, we typically see less of the sky. But this matches our stars plus sensitivity approach, so it actually matches quite well. It also helps with RFI because now we're more sensitive to a particular point of the sky instead of large points of the sky. But ideally, I was going to say that the large satellite constellations are changing that. And finally, it's kind of payback. Even the optical astronomers are upset with satellites now. We radio astronomers have been upset for decades. And I mean, not that I wish it upon the optical astronomers, but it's affecting all of us now. So ideally, we would see a large chunk of the sky at high sensitivity. But sensitivity is computationally very expensive, except if you use a big dish. But happily, that will get better with time as we become more computationally inexpensive, and hopefully figure out how fusion power and things so we don't warm up the planet, or we take all the things that the Bitcoin mining people are doing and leverage towards SETI. And I've seen all the sky all the time, sees all the RFI in the sky. That is unhappy with time. That only is going to get worse. There is some speculation at some point everything will be optical fiber. There's always going to be RFI, and it's always going to get worse. But really, we want everything everywhere all at once, without the hot dog fingers. All right, so what do I think is the most likely signal that we'll detect in the near term? Well, I think it'll be fleeting. I'll talk about why. It's obviously from an unknown direction. We don't know where they live. And an unknown frequency, we don't know what frequency bands they use. So why do I say fleeting? Well, sometimes the universe, conspires to make them more detectable. For instance, interstellar medium scintillation effects. This first plot here shows this isn't thermal noise. This is actually scintillations in the interstellar medium where you actually get focusing and defocusing effects. So maybe there's transmitting, we can't see it, and all of a sudden the interstellar medium goes around, and they're bright. And we have to be ready we don't know where that's going to be, what frequency, or when, so we have to be ready for it. Right now, with all the planets that we're discovering, we're now can look for things that might line up. For instance, the TRAPPIST system was brought up. Well, there are planets there, maybe if they transmit to one another, and we happen to be in line, that will be a fairly fleeting, but arguably they're going to put a lot of power in transmitting to their family back on the other planet in their solar system. And finally, maybe they are trying to be deliberately found, and they are beaming out, but it's on a schedule. So, you have to go to the galactic directory of transmissions and find when you can phone home to Earth and when you're going to transmit to Earth. And so that will also not be all the time, and we want to be ready for that. We can throw interferometry at it. That helps a lot. It separates the sensitivity resolution problem, but it's more immune to RFI and so on. But we still can't see through RFI, and it doesn't solve everything. And we have this goal of all the sky, all the time, all frequency, and handle all RFI. So what do we do there? And then we want to learn and expand. We're going to learn things we continually do. How can we make it better? So obviously, the next great place to go that handles the RFI issue primarily is the far side of the moon. All the sky, and no, there's an asterisk, because we actually know that there's some RFI probably. Well, we know there's some RFI there, but it's pretty good. It's countable as opposed to the Earth where the RFI is essentially infinitely uncountable. In terms of going to the moon, we are at a tipping point. Kennedy said we're going to go to the moon at the end of the decade and do the other things. Well, we didn't really do the other things, but now we're at a tipping point. We're going to go to the moon and we're going to do the other things. And so we have a lot of things that are conspiring to make it accessible to us. We also have a reason to go there, in that the RFI. So the first one, we have with all the wireless communications, orbiting, going around in all our pockets. I mean, I'm a disaster. I'm an RFI disaster. I have a Tesla, and it radiates all over the place. So, I'm a bad guy. But we don't want to get rid of it. We love our technology. Even when there's a significant investment in infrastructure and policy, like the Karoo region of South Africa, where I have a telescope, Australia, where I worked on a telescope, they're still not immune to RFI, and I often call satellites the great equalizers. They really make everywhere on Earth essentially equally bad for radio astronomy, but we love them anyway. But fortunately, the advent of accessible and relatively low-cost access to space means that we can deploy telescopes in space that aren't the great observatories. We're not in a period where we have to have a multi-billion-dollar great observatory to possibly go to the moon. Part of this is leveraged by the commercial space sector. The aforementioned Tesla founder guy is pretty, I guess, helpful, as well as the NASA programs, primarily the Commercial Lunar Payload Services, or CLPS. So at the Breakthrough Listen, we've actually gotten a pre-phase A study to try to develop a very strong proposal to put a preliminary telescope on the moon to get there before everybody else and see what's going on there before the masses arrive. We do know people have already been there. This has already been shown, the Chang'e 4 landing in 2019. I believe it operated for a few weeks. Fortunately for RFI management right now, things don't keep operating on the far side of the moon. So they go there, they do something, and then they crap out. We're not going to be able to rely on that. So NASA has a timetable and a program. This is a beautiful NASA illustration. They do amazing graphics of the telescopes going to the moon that are ostensibly part of the Artemis program, but there's manned and unmanned person and unperson lines here. These are the telescopes that are going, or the payloads, I should say. I have telescopes, obviously, I have one-track mind, that are going to the moon, and it started. Earlier this year, Peregrine 1 went off a brand new rocket, the ULA rocket. I was actually fortunate enough, I was invited to attend, so I was able to go and watch the launch. It was all very exciting. Later that night, they weren't quite as excited as the Peregrine one, didn't quite meet their expectations for a full mission success, but they still learned a lot. IM-1, which did land on the moon, kind of got tippy, but it made it to the moon, so it's going there. Another one I want to highlight, I keep pressing the middle button, is Lucianite, which has been mentioned a few times, which I'm also involved in, and it's down here, so it hasn't gone. The first two have actually gone. This one is down here in the queue. It's definitely going, and has, it will be the first, well, the second telescope to deploy on the far side of the moon. This guy, also landed on the moon. It's very, you can tell this is like the pluckiest lander ever. This picture's amazing. But we know more's coming, and so we want to be able to manage that, which is what this whole conference is about. And it's not just landers on the moon, but the data have to get off the moon. Now we know the Lagrangian point is very useful for that, and we park things at the Lagrangian point. It was fascinating to know that Turin has that great connection to Lagrange. I hadn't known that. I think that's wonderful. It's fascinating. And all this is happening. We've got a guy back there who's going to deploy a relay around the moon. He's doesn't even know I'm talking about him, but he's putting the L-band pathfinder that will bring back the Lucianite data. So we want to get there. We think it's kind of important to get there and see what's there before all of this traffic. So we're proposing a telescope called the Lunar Farside Transient and Technosignature Telescope that I abbreviate LIFT-3. We want to get there soon and take baseline measurements before the crowds arrive. And we're trying to land before the end of the decade. 2028 is the target landing time. So this will do unique science on the moon in the near future, and we hope it will augment activities to understand the lunar far side and not pollute. Obviously, we have the greatest incentive to be the cleanest RFI and person up there. We also want to do pathfinding for future lunar observatories and also look for other smaller projects that might address science and technology. So as we know, the lunar far side is only going to get busier, and we think it's important for someone to go there earlier. And I'm glad it actually came up a bit later because I think it is important to address out-of-band emissions and harmonics. I will point out that the most powerful signal in the Kourou that we've ever seen from my low-frequency telescope is a power filter that went bad, and it outshone every other intentional transmitter on there. The Chang'e 4 issues were mentioned about the pollution. There was also a European satellite that went to study the sun that also had these same issues. And hopefully Lucianite, and I feel confident Lucianite will address that, but in fact, they're not removing all the RFI, they're just putting it at known harmonics. So harmonics and out-of-band emission are key to understand and make sure that we handle that, because again, the power systems for the low frequencies especially are incredibly powerful and are much brighter than really anything else other than a directionally intentional transmission. So I would urge to make sure we have out-of-band emissions and harmonics as part of any process we do here. All right, what's the scope of this telescope? This isn't an observatory. This isn't something that will be deployed. It should be containable on a lander platform. It should be targeted toward bands that we can't do from the Earth, at least do from the Earth well, so out below the frequency cutoff of the atmosphere, as well as the particularly contaminated bands on the Earth. Have tiered processing, because you can't get a lot of data back. Maybe in the future you'll be able to get high-def TV back from the far side of the moon, but now, happily, actually you can't. All right, so in terms of what the environment is like on the far side of the moon, there has been an experiment on a NASA Explorer 49. I live in San Francisco, so I love the 49er aspect of Explorer 49. That was a low frequency. You can see over here the frequency is 10 megahertz plus going, and then once it goes behind to the far side, all the RFI goes away. So that was pretty good. That was 1975 was this published. So part of the push here is to get another telescope. Someone asked me, well, what if you get there and there's a lot of RFI? I'm like, well, we want to know why there's a lot of RFI on the far side of the moon. In terms of bands to look for, again, below cutoff, since you can't do it from the Earth, the cutoff is about 30 megahertz. It sort of varies between 10 and 30 megahertz. As part of this, see, I'm doing everyone else is going too far. As part of this CLIPS train, I call it the CLIPS train, there are low frequency precursors and telescopes going. Actually very soon, something called ROLSIS isn't really going to do astronomy, but it is going to look at the lunar regolith in terms of efficiency of making this telescope, and have the ability to do some, as well as Lucenite, which has been mentioned, and which is quite deeply involved in Lift 3. Fortunately, being at Berkeley, if I want to go to someone that knows how to do something on the moon, I've got the Space Sciences Lab, and actually Stuart Bale, the PI's office, is just a few steps from my office. So we want to target that band. We're going to use a lot of the Lucenite hardware, or at least the concept, because it's been developed. It's already developed to fly in space, and it's essentially ready to go. So we can leverage that. And so we're going to target a band from 1 to 50 megahertz, a single dipole that will actually be essentially the same dipole as Lucenite. And we hope to get there in time, and Lucenite is still operating, that we can actually do interferometry with Lucenite. So we're going to land close to Lucenite. Not within 2 kilometers. 2 kilometers is kind of the spacing that people want to keep, but we can land. These people tell me they can land within 5 meters. And in fact, the upside down lander landed within about 5 meters of its target location. So you kind of only need 1 antenna at this band if you're going to have it be deployable on a lander. So what do you do with the rest? I'm involved with a telescope called the Allen Telescope Array in Northern California, so I thought, well, let's just go out. And so actually, the night before I left, I said, well, I'm just going to go out and point it and tune it to about the lowest frequency we can detect. This is just using an SDR. This is just pointing around at about 600 megahertz. And you see a lot of RFI, and it gets better and worse. These are actually not places where the RFI went away. These are called waterfall plots. This is frequency, and this is time. The RFI didn't go away here. The band is bigger than this receiver band, and so I think it more likely completely saturated over those parts of the scan. It looks a little worse. It looks more a little appropriate if you actually plot it. So this is just that same data plotted. And you see in this 122 megahertz band, no matter where you point in the sky, it's bad. I mean, it's good for humanity. We use all that information for various things. But SETI is virtually impossible. Even with an interferometer, a widely separated interferometer, to do it with under that. This is another telescope I'm involved with in South Africa. It's an epoch of ionization telescope, so it observes at the lower frequencies. And this is a frequency here and time again. This is another waterfall plot. And you see all these bands that we wipe out. This is the FM band. It's not white like that because there's no RFI. It's white like that because we actually just excise the entire RF band. In fact, bands on either side of it. So FM is also inaccessible for SETI on the face of the planet. So that will be another band that we want to do on the lunar far side. This is another telescope on that same site that Hera is, the Meerkat telescope at a higher frequency. And these dark bands that are shaded out are essentially flagged out for RFI purposes. This is in one of the quietest places on the planet for this sort of astronomy. So the proposal for Lift 3 is to have an array as well as a few single antennas. The array is going to be focused around the UHF, primarily because that's where we have the maximum in sensitivity that we can get because of the galaxy and electromagnetics. So we're going to look at about 30 element array with making about 12 beams. It's this big shaded area because the sensitivity, this is good sensitivity, this is worse sensitivity, I should say. It varies quite a lot because of where in the galaxy we're looking. This curve is looking at these quiet spots that were brought up earlier. There are quiet spots in the galaxy, and in fact, this is where Hera, on the southern hemisphere, where Hera and the MWA target for the epoch of ionization studies, and you get pretty good sensitivity. But when you're pointing in the galactic center, your sensitivity goes down because it's so loud. But there's a lot of stars there, so for SETI, we're quite interested in that part of the sky. This is the low frequency band that is going to be the Lucenite clone, the FM band, and broadened. And then you're going to the far side of the moon. You might as well throw another antenna on and get more bandwidth. So this is a factor 2 scaling on this, just to go through all the way up to about 1800 megahertz. And again, do the first studies and see how the RFI is looking. So going to the moon early on, you don't have a lot of room to play with. So our specifications, fortunately, they all became very easy numbers essentially. Something I can remember. We're going to have the telescope has to be 100 kilograms. That excludes the batteries. We get to use all of 100 watts during the day and maybe 40 watts at night. So we, in fact, may not operate all the array all night. We get a whopping 100 gigabytes a month data return. That's the Lunar Pathfinder value, essentially. And we're targeting 100 weeks of operation. And we want to land before the end of the decade. I feel like I should say decade to try to do my Boston accent and say before the end of the decade, but I don't do a good Boston accent. So this is just a schematic of the array and the beamformer hardware, some of the other TT&C, the Lucy heritage hardware here, and so on. And it might look something like this. This actually uses Vivaldi's. So again, this would fit right here. And it's the entire payload. So that's the hope. It's the pre-phase A funding has been studied, and we're hopeful that in the next year or so we'll have phase A dollars and maybe go forward with this. So hopefully you'll hear a lot more about that. Now, one of the reasons why I'm here, I've been talking to people like actually Alana, was at a Breakthrough Discuss meeting, Adam Smith, a Department of State lawyer, is to make sure, we want to make sure we're doing things in accord with, current best practices and so on. So those discussions will continue. And of course, us more than anybody want to have good RFI specifications because that's the whole point of going there. So that's what we hope to do in the near term, and hopefully a motivation of why in the near term you want to do technosignatures from the far side of the moon even before we have these large telescopes. But again, the likely future for the far side of the moon is these big telescopes and big infrastructures, and maybe maybe we send our grad students there in the future. I don't think quite for you, but my wife actually asked me, well, do you have to, I travel a lot, and she's like, well, if you do this, do you have to go to the moon? I'm like, no. So just to highlight, one of the, kind of a phrase that goes in the back of my mind, and the importance of what this symposium is trying to do to allow this science to continue as the best it can. Thank you.
Thank you, Dr. DeBoer. So we have plenty of time for questions because next talk is tomorrow morning. So.
Tell you something. Thank you. Let me tell you something, and this also possibly is good for the two radio astronomers over there. I don't know. Anyway, I was at Berkeley before you and I met, and I left about 100 copies of my old book called the KLT Relative.
Yep, we have it still in the lab. Yeah,
You haven't seen that.
we have a few left. We've given them out, but
Thank
there
you
are
so
a few
much.
left.
I appreciate
So
it.
if you want a copy of his book, if you come visit us at Berkeley, we still have copies.
Thank you. Appreciate it. But let me say a few more words about that. Why am I been concerned with this? Well, quite simply because I was looking for a transform better than the Fourier transform to reject RFI of all kinds. And so the conclusion is that, in plain words, this thing is the mathematics of quantum physics, that is eigenvalues, eigenvectors, and all that, applied to signal processing, essentially. So the idea is basically that we believe at the beginning, we separate the time behavior from the probabilistic behavior. And we make an assumption saying that whatever comes inside the radio telescope is noise, basically. Of course, there may be the signal inside, but who knows? So this is the first step. Then we compute numerically the autocorrelation of that for a finite time between 0 and capital T. And that means that we are avoiding these tricks that plague the Fourier transform, Henning windowing and all that. And then, when we have done that for a finite time, we perform a principal axis transformation on the autocorrelation matrix of whatever has come inside. This is the very demanding mathematically part, because unfortunately it doesn't go as n log n as we all are used in classical Fourier transform, but it goes with n squared. Nevertheless, today we have very powerful computer, so I think it is feasible, at least in some cases. So my conclusion is would you apply this for any of the future space mission to the moon Farside that would increase the capability of RFI rejection? Thank you.
Yeah, particularly in the future. As I mentioned, I've always been a big fan of the KLT, and on the lunar far side, we might even be able to do something as simple as kurtosis, which is we do to detect RFI on the Earth. But on the far side of the moon, maybe we can do kurtosis studies to find ET, because there's no other RFI, and it is truly Gaussian noise. But things like the KLT, looking for non-Gaussianity in various ways. And so I kind of went back to this slide because, well, I guess the previous slide, too many. So currently, as part of this, we do the simple modes. CW, it's actually a drifting CW, but it's a continuous wave signal. Ideally, we have a universal demodulator, and a KLT or a fast KLT sort of works that way. And as I mentioned here, happily, those all are going the right direction. In terms of on the far side of the moon, I mentioned a tiered approach of data. So if we want to do a lot of processing, we want to pull a little bit of baseband and send it back to the Earth, and we'll do that. So we can save tens of seconds of data, and then we spend that month getting it back to Earth, and that will be part of this tiered approach, so that we can now look at this data with a lot more tools on the Earth. But we want to do more than that. We don't want to go to the moon, spend $150 million, and that's the shocking thing is $150 is a completely reasonable budget for this thing. I didn't highlight. We've gone to all of the lander vendors, and I have numbers from them. I mean, admittedly, they're trying to get me to work with them, but they can all do it for $150 million, which is quite remarkable. So we don't want to go there and spend that, be there for 100 weeks, but only use a minute worth of data. So then we're going to store higher cadence frequency spectra, and then send that back slowly. So that's the second tier. And then hopefully the lunar far side is so RFI quiet, we can just do diffs on that on some cadence. And that will be hopefully, potentially very infrequent. But what we'd like to do is send enough baseband data back so that we can look at some of these techniques like a KLT, kurtosis, and other things, and see how amenable it is to truly sky noise that is well, unless there's something else in there, it's Gaussian noise. But yeah, that technique is fantastic. I actually, as a graduate student, one of my fellow PhD students used the KLT to do retrievals of wind direction over the ocean in the principal cantonades. And at that point in time, I hadn't seen it before, and it just seemed like magic. It's an amazing mathematical technique. And she was able to determine from microwave radiometer in space the wind direction based on the asymmetry due to sea foam off breaking winds. Anyway, and this was the KLT.
Let me just mention one thing. Tomorrow, I am going to bring 2 copies of the book that he was talking about for you, gentlemen. Thank you. And also for the lady over there.
And now I think I'm between you and beer, but
First of all, thank you for the presentation. And I wanted to remark that I'm Lorenzo De Piccoli. I'm a historian of science. I study history of astrobiology, and I recently did my master's thesis in history of SETI. And so, first of all, as a science fiction fan, I wanted to say that this is basically the plot of the Sentinel, the short story by Clark, but in reverse. Yeah. Instead of going to the moon and finding the artifact, we go to the moon and put the artifact there to hopefully find more. And my question would be concerning it's basically more of a curiosity of mine. I wanted to know if there is some discussion among radio astronomers and scientists who are working on projects such as these regarding the nature of the technosignatures that are expected to be found. In other words, one major epistemological problem and one major epistemological critique that is addressed at technosignature science is that, well, once you find an anomalous phenomenon that could be regarded as a technosignatures, how do you rule out that there are instead natural phenomena that we simply don't know yet that could cause that same object observation? Like, I'm reminded of the case of Oumuamua, the controversial case. Right. And for example, thank you.
So for Breakthrough Listen, we've been going for about 7 years on all the major telescopes, or many of the major telescopes in the world. And so that's a lot of SETI. We've had one signal that made it to a human consciousness for us to look at. Unfortunately for us, got out in the press, which so far I've been involved in 3 potentially interesting signals. All 3 of them have been in the press within hours to days, so I don't think we're going to hide any SETI signal. We give this detection, though, we call BLC1, and it was a great test case for us. First of all, didn't like the press scrutiny so much because, fortunately, the early stories were fairly responsible. We didn't want to, there were no claims it was ET, just that it merely satisfied the first stages of deployment. So then we spent, basically 3 months, the entire team scrambling to try to explain it, looking at drift analysis, looking at harmonic analysis, and looking at different techniques. And it was a boot camp for, okay, what might you do if you detect something like this? Now, an ideal SETI signature repeats. If you know about fast radio bursts, they're great to study in more detail because some of them repeat and you can look at them in more detail. But if it doesn't, we'll just have, the equivalent of a wow signal. But of course, now we record more data. And so based on that 5 minutes of data we had, it was actually more than five minutes, we were able to look back at the data and do, like I said, a number of analyses. And finally, a fairly detailed and sophisticated harmonic analysis showed it was related to other RFI, like to less than a hertz that we knew was local. So that was why we were basically fairly unequivocally say this is Earth-based. So I think for a SETI detection that you can't keep looking back and having telescopes all over the world really look and understand, you're going to keep throwing ideas at it to try to disprove that it is an ET. Because even the drift analysis, which we've never seen, so here we have something that's passed our on-off tests, just coincidentally, actually, turns out. The harmonic analysis, the drift analysis, sorry, everything was in about the right order of magnitude to potentially be sidereal. Had the wrong sign, which is interesting, but maybe they're just messing with us and inverting the sign or something of the sidereal rate. So even that looked pretty interesting and pretty good. But then this harmonic analysis, and then we were able to essentially stop. There are 2 papers that came out about that of how you might do it. If we have this commensal SETI where you have all the telescopes all the time looking, ideally you have it in multiple independently. But again, with RFI, these telescopes are increasingly going to have to be on the far side of the moon. Because, as you saw in this, you can't do SETI through the RFI. There are gaps in there, and you can do SETI in all these bands to varying degree. But you want to save the data. If you make a detection, save as much data as you can, and then throw every tool you got to try to disprove that it's ET. BLC1 was a lot of fun, but like I said, it was unfortunate. We still don't know who leaked it. No one on our team leaked it, but it made for an interesting few, because it made all the papers, and the scrutiny got a little uncomfortable.
So this was the last talk for today, and before closing this first day of the symposium, just 2 more things. First of all, I would like to thank the guys from the Aerospace Engineering Students Association from Politecnico di Torino, which came here today, and they will be here tomorrow, and they support the organization. So they are the guys that you saw in the room or in the reception desk. Okay, they are still there. Okay, thank you. They also found water on Earth for us. And the second thing is that we would like to invite speakers of today for a picture here in front of the desk, since we don't know if you will be here even tomorrow, so maybe we can have a picture here. Sorry?
All of them.
Yeah,
Today's speakers
yeah,
and tomorrow's
yeah,
speakers.
of course, all the speakers that are here in the room for today and tomorrow. Okay, the second day will start tomorrow morning at 9:15, 9:15, 9:15. Always here in this room. So enjoy your evening here in Torino. It was a pleasure to have you here, and hope to see you tomorrow. Thanks again. Okay. Sì.